Okay, so we have an easy problem here. Let's take a look at what we're given here. You're given an integer, money. So money is an integer, yes. Denoting the amount of money in dollars that you have, and another integer denoting the number of children that you must distribute the money to. You have to distribute the money according to the following rules. All money must be distributed. Everyone must receive at least $1, and no one receives $4. Return the maximum number of children who receive exactly... I guess this means no one receives exactly $4. Return the maximum number of children who receive exactly $8 if you distribute the money according to the rules. If there's no way to distribute the money, return -1. $20, 3 children, output is 1. The maximum number of children is $8 will be 1. One of the ways to distribute the money is 893. It can be proven that no distribution exists such that the number of children getting $8 is greater than 1. And then we can't do, for this solution, we can't do 8, 8, and 4 because we can't do 4. And they have to receive exactly $8. 16, 16 would be, and there's 2 children, that would be 2. Okay. And then everyone has to receive at least $1. Okay. All money must be distributed. Okay. Let's think through this then, because a bunch of random rules here. I will say that I'm surprised that it's easy, but I think once you know the algorithm, it probably becomes very easy. The money is always between 1 and 200, and the children is 2 to 30. So those are the constraints. So, I think probably want to consider like a naive solution. And I'm also thinking that we kind of have to be greedy here. I'm also thinking potentially there's a recursion aspect to this. So lots of things. Do I have an interview soon? I had an interview that was set for 15 minutes ago. But they literally canceled this morning. I emailed them. I was like, hey, what happened? Did you do you want to reschedule? And like, actually, we wanted to hire 2 people. We already hired them. So I didn't even get to, put my case to them. So unlucky. Bad timing, I guess. But like I applied to 16 jobs yesterday. One of them was that one. So hopefully something happens. Somebody gets back to me. Yeah, it's big oof. But just gotta keep pushing. I'm also trying other avenues. I created a Preply account. Maybe I can tutor people. I do like teaching. So something to consider. In the meantime. But back to your problem. This seems like it has the potential to be a simple division and subtraction. my intuition tells me that this could probably do, and we could probably do this in constant time. No looping required. So the first step is make sure everyone gets $1. So basically the money minus equals children. To me, that's the simple approach. And then we got to be greedy. How many children can get $8? And so given that we've already given everyone $1, the count would be the floor of money divided by children. But we're basically done here. We're basically done, but we got to consider this last one, that nobody receives $4. And basically the way we could detect that is if we basically after we were so greedy, we need to figure out the money that we have left and how we can distribute it to the children. Given that the rest of the children only have $1 already. So I think money at the very end, we're probably gonna have like some kind of condition that makes it so that it's either count or count minus 1. But we need to detect money but then we also, if the money can't be distributed, we get -1, which is strange. Basically, if there's, I guess, 0 children, the count is 0, then we give -1. Children, no, count times 7. So this will be how much money we have left after we've given those children, so with this greedy algorithm, $8 each. And then we have to do this detection. Basically, like, to me, I don't see any reason why, like, if there's at least a child, if there's more than 1 child, then we can guarantee that they won't get. Oh, but then I guess then the question is, what if there's so much money? There's so much money that nobody gets $8. All the money must be distributed. That's another really important condition. Hey him, welcome back. Thanks for the encouragement. All money must be distributed. Alright, we'll have to think of that edge case. So the edge case is lots of children, or lots of money. Return the maximum number of children who receive exactly $8 if you distribute the money according to the... If there's no way to distribute the money, return -1. This part makes no sense to me. If there's no way to distribute the money, so it's basically asking you to never return 0. It's either return -1 or a positive number. So how many children get $8? Like, so one of the things at the end, if because there's nothing stopping a child from getting like $1 million, right? So something to the effect of, if count is less than children, or sorry, if count equals children, and there's if children equals 1, I feel like there's gonna be like edge cases here, and I'm just trying to figure out what those edge cases are. Month for some reason. All money must be distributed. All right, let's deal with all money must be distributed. Basically the idea is if there's still money left over at the end, then we'll return count -1. Basically, the idea here is our child, and we'll do, this is dirty, but if there's any money left over, then we just got to take all the money and just give it to one of the children. And every other child will still get $8 except for this last child. That's the idea. And for this one, we need to look at the remaining money. I think there's also just return count. I think we've considered lots of money at this point. Nobody receives $4. So basically, if the children minus count is greater than 1, or the money is not equal to 3. Basically saying there are children to distribute the money to. Actually, there are no children to distribute the money to. Would be children minus count equals 1. is only one child to distribute the remaining money. So if there's only one child to distribute the remaining money, and the remaining money is $3, then we actually return count -2, because not only can this child who's getting 4 not receive that amount, the child before them, we need to adjust the amount of money they're getting in order to give this child who's getting 4 the correct amount. So, and then if that's 0, then it's -1. I'll put one child left. If there's one child left and the amount of money is $3, then we need to redistribute the money between the last 2 children. Which actually it's just count -1, right? Because we've already counted these 2 children who have $8 as having counted. It's this last child who we need to. So we're removing the second to last child. Something like that. So all money must be distributed, that's this condition. Everyone must receive $1, that's here. Nobody receives $4, that's this condition. And then I guess this very last case, if we return 0, we should return -1. If either this is correct or I don't understand the question. Okay, maybe I don't understand the question. Okay, so we have 20 monies, 3 children. The output is what am I outputting? What am I outputting? Maximum number of children who receive exactly $8. Okay, I put 4. Should have gotten 1. Okay. Oh, this is probably. How am I possibly gonna be outputting 4? I guess one thing I didn't consider were the count. Max dot, not that max or min. So, thinking about this, money is 20, children is 3. It should be like 2 point something, which would become 2. This would be 2. Do we need this? Two is the count. Like, am I really bad at math? Wait, what am I doing? Okay. I don't know why I did that. Mathematic. Okay, so thinking about this becomes 17. And then this will be 17 divided by 7 is 2 point something, which becomes 2. Money minus equals count times 7, which gives us 14. 17 minus 14 is 3, so money is $3. Then we will detect this edge case, and then we'll go down this one and make it 1. Okay. Okay, I just put the wrong variable there, the wrong value there. We can submit it. I'll put -2. So if the money is not enough, so we're going down one of these, probably this one. I think to make things easier, I'm gonna do function intermediate and just simplify this. And then in here, we'll do return intermediate. Same arguments. Intermediate, money, children. And we'll do math.max of -1, -1. That way we don't have to write this expression everywhere. We're able to remove it from a lot of places as well. We're going to run it against the 2 test cases just to make sure. And then we're going to submit it. Expected 0. Wait, what am I? The maximum number of children to receive exactly $8. Okay, so I am not understanding this question correctly. Let's go back to my submission. It should be 0. I got -1. Okay. You can give 1 to each of the 2 children. Yeah. Give 1 to each of the 2 children, return 0. But no one gets 8. Yeah. Okay, I thought that at least one child had to get 8 in order to trigger. So the main thing is that no one gets 4. Okay, complicates things a little bit. Okay, so we start off by giving people money. We'll end up with 0 money, it'd be 0, count 0. If there's 1 child left, then there's 3 monies. Okay, and then we're doing this or -1, which is 0. This one I feel like this is probably the most complicated condition. Nobody receives $4. because you have a choice of not giving people $4. So you basically need to be able to detect, there's the case where there's enough children to distribute so that they don't get $4. But then there's also the case in which I guess there's one child and there's only $4. So if there's one child left and there's money to distribute, but the other thing is if there's one child and the count and the okay, so children equals 1. If there's one child in general and money equals 3, then we return -1. Something like that. But it didn't run last time. Submit. Output is -1, expected 0. Okay, let's run that then. So every child gets $1. The count is 0. There is one child left. There's 2 children left, so we don't go down this one. But there is money left over. Probably this. Maybe we don't need this anymore. I feel like that's cheating now. Okay, in that case, we could just bring this code back in. Alright, let's run it. Submit it. Oh, I'm still getting -1. For this one, there's not enough money. So the money ends up being negative, which is interesting because that could affect the count if there's so many children and no money. That could affect the count. So I'm gonna have to do this to handle the cases in which there's way more money than... Yeah, we keep going. No giving up. So thinking about this, one child left. We don't go through this because we have 2 children left. There's one child in general, but okay, we won't go down this because we're doing this max now. I think money was -1, which is causing us to go down into this route. I just wanted to see if the base tests pass. We could submit it. Still -1. Okay. Let's like start plugging stuff in. 1, 2. So this will be money minus children. So money is now 0. Account will be money divided by 7, which is 0. This is still 0. Children minus count, which is going to be 2 minus 0. This will be false, which means we don't even check the money amount. This will be false because children is 2. And then money is 0. Money is... just put it here for now. We're gonna go false there. All money must be distributed. The money should be 0. And then we return count. I would expect a -1. Oh, because every child needs to get $1. Ooh, that's a requirement. Everyone must... okay. We don't need that, Max. We need to do if children is greater than money. Return -1. And then the rule that we're satisfying here is everyone must receive at least $1. Cool. Let's run it for the base cases. And we'll submit it since it passes. Okay, there's more. Alright, just thinking about this. I feel like it should be 1, but we got 0. So let's see if we can figure out why we got 0. So the values here are going to be 10 and 2. Is children greater than money? I'm just gonna reverse this just so that the variable names align with each other. If there's not enough money for every child, return -1. Money is 10, which is not less than children, so we continue. Next, we give each child $1. So money is... we're gonna go back to minus equals. Money will become 8. And then count will be 1, because 8 divided by 7 is, and flooring it is 1. So then the money becomes 8 minus 7, which would be changing this to be 1. Okay, so if there's one child left, is there a child left? Children is 2 minus count, which is 1, gives us 1. There is one child left. Is the money equal to 3? Money is 1, so it's not. We continue. So this is false. Actually, this was true for this. Is there generally one child? No, that's false. And then finally, is there money left over? There is money left over, but I guess this is a little bit more complicated. If there's money left over and there's not one child left, then we gotta say, okay, well, one of the children gets screwed over, and they get the minus. They get excluded from this because we want to max it out. This last child actually doesn't get gypped because they get all the money. They get the rest of the money. Alright, we'll run it. I'll submit it since they passed. Oh, there's more. Okay. Expected 1, which I understand. I agree, it should be 1. 11 and 3. Is money less than? No. Money minus children, so money becomes 8. The count will be money divided by 7, which is 1, which is still 1. Is there 1 child left? Count is 1. Now there's 2 children left, so this is false, which means we don't consider this. Is there 1 child in general? No, that's false. And then... okay. We could say... more children equals... children... it's gonna be... children is greater than count. If there's more children... no more children. So if children is equal to count, if there's money left over and there's no more children, then we have to give all the rest of the money to one of the children who did get 8, and therefore we have to decrement the count. Let's run it again. Let's submit it. Dang. We got 3 somehow. Let's run it. Let us run it. 23-2. Everyone must receive $1. 23 less than 2, it's not, so we go over that. Money minus children, so that becomes 21. And the count becomes money divided by 2. Or sorry, money divided by 7, which is 3. And that seems like a problem. Seems like a problem. Maybe, am I doing the math wrong? 23. Yeah, I am doing the math wrong. This is 23. There's 2 children. 21. This becomes 23. Yeah, I'm doing... This got too big. So we do need that somewhere at least. So that brings us down to 2. This would be 14 minus 21 is 7. One child left. There is not 1 child left. There's no children left, so we don't do this. If there's 1 child in general, that's not true either. And then there's no more children, which there's not. 2 is 2, and there's money left over. Then we have to decrement. I think we can get rid of this. So ultimately the issue was this count was exceeding the number of children and probably giving us a negative number at some point and messing things up. So let's run it against the base test cases. And let's submit it. Alright, we finally did it. The only question at this point is, can it be improved? Everyone gets at least $1. Make sure everyone gets $1. Give everyone $8 that you can, and then figure out at the very end who you can't give that money to. Okay. There's nothing, it's, you know, it's constant time. Doesn't matter what the value is here. This all runs in constant time, so there's no real way to optimize in terms of complexity. So I'm just curious what the solution of others were. How about this? I'll try it in a second. Let me see what other people did. Ooh. This is clean. Okay, so they give $1 to each child. If there's not enough money, then they return -1. Then they do they see if there's enough money for every child and that the money is evenly divisible by all the children. If that's the case, then we just say children. Very easy. If the amount of money for the children... Okay, interesting. So if there's enough money for children -1, this one's a little harder to reason though. I gotta stare at it for a little bit, because yeah, this evaluation can get kind of out of hand. Oh, what you floor it? Money divided by, and then money mod 7 is 3. Pretty much. But like, what if there's a lot of money? I almost wonder if this one, how necessary this one is. It's so specific. But I guess you do need it. You just need to handle this one edge case of, okay, is there enough money for everyone but one child? And then that child doesn't get, it's basically, it's the edge case of there's one child left and that child gets $3. If there's one child left and that child gets $3, then we actually have to remove two children. One to account for the one who was originally getting 3 and one to help to distribute the money out. And then there's this one. This is easy. This is easy. It's easy, but in my opinion, it's easy to, in terms of complexity. It's hard in terms of understanding the problem. So like, yeah, the description is like, it has all these different rules. All money must be distributed. Everyone receives $1. Nobody receives $4. How many children get $8? Return -1. There's all these different conditions. Yeah, implementation is hard. So like, I had to put comments everywhere. I had all these different checks and conditions. So yeah, this is really clean. Wait, why can't I click on it? This is a clean solution. And if you just like kind of know the math, then yeah, you could just write it This one, they kind of, there's no like clean, really clean, simple way to write this. Like, even though this is clean, it's just really hard to reason. It's really hard to say, why did you write this line? Why did you write this line? More variables or comments might be helpful here. Like caching this value might be nice. Could be something to consider. Caching this value could be nice. Something else you could consider. Yeah, because you do this math floor divide 7 so many times. They probably could have gotten 0 milliseconds if they did that. Maybe. But yeah, that'll be that.